Alright, so in this rather short segment we're going to have a quick look at the geometric properties of the mutual inductance. You remember mutual inductance is useful in situations where we have two loops, let's say loop 1, loop 2, loop 1, loop 2. Loop 1 produces a magnetic field that threads loop 2, and the quantity that we're interested in is the integral of B1 dot dA2. And we're going to rewrite B1 as the curl of the vector potential A1 and explore what we might find out as a result. So let's do that. So what we've done here is we've rewritten B1 in terms of the curl of A1. We've substituted this into this equation, so there it is, and we've used Stokes' theorem to rewrite the surface integral as a line integral. We've now formally written out the definition of A1, and A1 at position R is given by this formula, and we've substituted this into here. Okay, this now gives us the integral of B1 dot dA2 is a double integral. We have an integral around loop L2 and an integral around loop L1, and of course the R in here now becomes an R2. You'll notice I've switched R1 and R2 here compared to here. It makes no difference because this is the modulus. There was no reason for doing this. There was no reason for doing this. If we now specialize to the case of I1 equals 1 amp, of course what we get is the mutual inductance, and there it is. The mutual inductance is this double integral. This is dL1 dot dL2. I should make very clear that these are both vectors. So we have to take the double integral of dL1 dot dL2 around both loops, and we're going to do this in an exercise and perform this double integral to get the mutual inductance. Now, really the reason for having a quick look at this is it shows you that the mutual inductance, which is a geometric property, is symmetric. In other words, if we were to put a current I1 in this loop and calculate the flux through that loop, we would get exactly the same result for putting the same current in this loop and calculating the flux of the magnetic field through the second loop. So it doesn't matter which loop you put the current in and which loop you take the integral over, you'll get the same result. Okay, so as I said, we're going to do a little exercise on this in a workshop, and it will make that point quite clear.